Okay, here we are at the top of Mt.Hood Express at Mt.Hood Meadows, looking at Mt.Hood, which is a classic cascade composite cone volcano, often called a stratovolcano. One of the things you'll notice when you're up here is the rocks are different from in the Columbia Gorge or down in the Portland Valley. That's because it's a different type of lava. What you got in the Columbia Gorge is basalt. Basalt is a very low viscosity lava. It floods across the landscape, and that's how the Columbia River flood basalts came to be, is fissures in eastern Oregon, Idaho, opened up and flooded the entire state of Washington and Oregon Central Basin with flood basalts. But the Cascades are a different story. Mount Hood, Mount Rainier, Mount Jefferson, Mount St. Helens, Mount Adams, all of them are composite cones, and the lava that they are made of is a little different. It's called andesite. The difference between andesite lava and basalt lava is andesite has a higher silica content. Basalt has about 45% silica, whereas andesite is around 60%. That makes andesite a stickier, more what they call felsic lava. And the one thing you'll notice looking at the andesite is it looks distinctly different from the basalts that you're used to seeing in the Columbia Basin. It's a lighter colored lava, less dense, whereas your basalt is very black. Andesite's typically light tan to, it can go to dark gray, but medium gray is probably your standard. And moving closer to the actual rocks, one of the main differences you'll see is the individual minerals are larger, whereas basalt has very fine pyroclasts and minerals, crystals. The andesite, much coarser, larger crystals. In fact, if you get the lighting just right, they tend to sparkle in the sunlight. But the andesite, actual individual minerals are a much coarser consistency than your basalts, which are very fine, high in magnesium, iron, whereas your andesite has a lot more hornblende, a lot more quartz because of the higher silica content. What you have here is what's known as scoria. It's still andesitic as far as its chemical composition, but what you'll notice is it's more pumice-like. In fact, a common term for scoria is, in fact, pumice. There's a good example right there. If it'll focus, what happens, what creates scoria versus your more typical andesite is during the eruptive process, there's more trapped gases, and the lava, the mixture, is a lot more frothy. It's got more gases and stuff. So, you know, think of cream. Whereas if you whip the cream and get lots of air bubbles in it, it's a more frothy mixture. And when this is erupting, this would probably be considered more like a spatter cone, where it's ejecting globs of molten andesite more explosively with more gas bubbles and things like that. And when it cools, it forms this more cinder-like consistency. So if you can kind of compare the scoria or pumice to right below here is a typical chunk of andesite, you can see the more frothy nature of it. Chemically, it's basically the same exact stuff. It's just altered in its physical structure by the way it was erupted when this lava at this particular spot in the mountain was erupting. So when you hear the term scoria, it's just another term for pumice, and the chemical process or the chemical makeup is the same as the surrounding lava. It's just the eruptive style was a little bit different. This had more gas trapped in it, more frothy. Of a chunk of scoria, pumice, you can see the structure of it, and then by comparison, right above it here, you'll see blocks of just traditional andesite lava. You can obviously tell the difference, whereas the andesite is smoother, more densely compacted. The scoria or pumice, a lot more fluffy, a lot more frothy in its makeup. Again, that's because of the nature of the eruptive process. The ski patrol shack at the top of Mt.Hood Express at Mt.Hood Meadows. This is a good spot where there's a good outcropping of andesite that's easy to get to, easy to see. Just panning across here will give you an idea of the structure of your andesitic type lavas. A lot of fracturing, a lot of plates. But as I pan to the left here, you'll see it drastically change in its structure to a big glob of scoria or pumice there. Again, just a different style of eruption. There was more trapped gases and things, a little bit more explosive, more like a spatter cone like you would see typically in more basaltic type lavas such as Hawaii, but it does happen with your andesite lavas too. And then panning down, there's the whining dog Riker, except little doesn't like not being the center of attention. And again, that's your andesitic lavas. Like I said, the main difference, the main thing that you can tell the difference between it and your Columbia River basalts, the color, typically lighter gray, whereas your basalts are either black, very dark gray, or even kind of a brownish. That's because of the oxidation of the iron content within the basalt. And then just picking up a chunk of it, super easy to tell the difference because of the size of the minerals inside the actual rock. With andesite, you'll see much larger individual minerals, a lot more quartz, a lot more hornblende than basalt. From Mt.Hood volcanism to Mt.Hood glaciation. All the glaciers at this latitude, this far south, are what are called Alpine glaciers, mountain glaciers. The ice sheet that once covered all of Canada and much of northern Washington during the last ice age never reached this far south. About as far south as that ice sheet reached was present-day Olympia. So all the glaciation you see in the mountains here in Oregon, specifically here on Mt. Hood, are alpine glaciers, typically what you see today in places like Glacier National Park. What we're looking at right here across this little valley is a small, kind of a glacial cirque, more of a glacial valley. At one point, a fairly large alpine glacier filled this little valley, carved it out, and then went down below. I'll pan over here, and looking down there, you can see the Mazo, little hut for getting brews on a nice sunny afternoon while skiing or riding. That's a small glacial cirque. That's kind of a terminus of this alpine glacier, where it pushed gravels and poorly assorted rocks into a glacial moraine. So that would be a small miniature version of a glacial cirque. Panning back up here to this rock island, you'll see, we're going to walk over to that area. A little hard to see from this distance, but you'll see lines carved downslope in that andesite. That's called glacial striation. That's caused by, as the glacier is sliding down the mountain, little chunks of rocks and gravel get caught between the weight of the ice and the rock, and the weight of that ice is literally grinding grooves in the bedrock underneath the glacier. We'll walk over there and take a closer look at that glacial striation. So that's a little bit about glaciation on Mt. Hood. Ridge, Mt. Hood Meadows, above the Mazo, above the popular ridge run, chunky swirly runs. And now that some of the snow is gone, still quite a bit for the middle of July, got got the exposed andesite here, and this is a real good spot to see the glacial striations, those longitudinal, downslope grooves that were etched into this bedrock as the glacier passed over it. So just kind of panning there, you'll kind of notice the pattern of parallel grooves, all of it running downhill. And looking down there. Then right below me here in the bedrock, some real good examples of cupping, carving, similar to what you would see of water carving out sandstone in a stream bed. But this was a glacier doing it. Panning over here, you can see the downslope grooves. Moving across. Riker checking things out. Okay, and then right in front of me, here's a pretty good example, fairly close up, where you can see those deep scratches carved into the andesite, all in one direction, going down slope. Like I said, that's caused by little chunks of rocks underneath the weight of the ice and just scouring that out, just scratching that bedrock. That's known as glacial striation. Real good example of glacial topography in an alpine setting. A bit lower, the last section of video showed this slab of rock from above. Here's a look at it from below. With the lighting, you can kind of actually see it a little better. Again, the polishing, the carving out, cupping of the rock, the andesite. And real pronounced here in this light, you can see that glacial striation, those long downslope grooves. Moving over here is just a beautiful example of it. Right there. That's just classic glacial striation. So during the last ice age, when this mountain was totally covered in glaciers, this glacier was traveling down the slope, down towards the Mt.Hood Meadows parking lot. And as it moved across this outcropping of bedrock, the andesite, which is obviously here long, long before the ice age, it cut all those grooves. And then here's the small little kind of a mini cirque, if you will. That slight little ridge over there, part of it is obviously some andesite outcropping, some bedrock. But if you look, there's the Mazo. If you look a little to the left by that light pole, you'll see a little ridge of poorly sorted rocks. There's gravels, rocks the size of your head, rocks the size of washing machines in kind of a loose pile. That's a small terminus, a small glacial moraine. So as that glacier traveled down the mountain, as it receded, that was a spot where at one point this glacier ended. And as it moved consecutively year after year, it would expand and contract with the winter and summer cycle. It would push that pile of gravel, glacial moraine, and form that small little hill right there. So basically, not super impressive, kind of a glacial cirque and a moraine all in miniature. This was obviously a pretty small alpine glacier, but enough to put some impressive marks on the landscape. And so everything, when you're up here at Mt.Hood Meadows and you're riding off Marmot Ridge on a good powder day, you've got an alpine glacier to thank for this really playful terrain that makes up this kind of U-shaped valley down the slope, all carved by an alpine glacier. A bit lower out of that wind, good shot of Mt.Hood. So some people might be wondering, why Mt.Hood, the mountain we all love? to hike on and ski on and camp on and all that. Why is Mount Hood here? Well, it's a volcanic story, and it involves plate tectonics. The reason the Mount Hood and all the Cascade volcanoes, known as a volcanic arc, exists is plate tectonics. The North American plate, the tectonic plate that the United States, Canada, Mexico sits on, is on what's called the North American plate. That plate is moving to the southwest about 2 inches a year. As it moves to the southwest, it's a continental plate. It is riding over the top of an oceanic plate known as the Juan de Fuca plate. The Juan de Fuca plate is just a tiny little remnant of the ancient Farallon plate. Farallon plate was a massive plate that subducted underneath the North American plate. It's responsible for creating the Rocky Mountains, the basin and range area of Nevada, the Sierra Nevadas, Coast Range of California, Coast Range of Oregon. But the Cascade Range is a volcanic arc due to subduction. So what happens is as the North American plate moves southwest, the Farallon used to, now currently the Juan de Fuca plate, is diving underneath the North American plate. Reason this happens is an oceanic plate is thinner and more dense. Continental plate is thicker and more buoyant. So in every case, a continental plate, when it converges with an oceanic plate, it goes over the top and the oceanic plate dives underneath. As that plate dives underneath the mantle, underneath the crust, it creates a lot of friction, a lot of pressure, a lot of heat. That heat forms magma. The magma rises up to the surface, comes up through cracks and fissures in the Earth's crust, and creates mountain ranges, volcanic mountain ranges, all andesite. Almost all of your volcanic arcs created from a convergent continental versus an oceanic plate result in andesitic lava, more of a stickier, higher silica content lava than your basalts that form in a shield volcano such as we see in the Hawaiian Islands. As that lava pushes up through the surface, it squirts up the andesite, and that is why Mount Hood, Mount Jefferson, Mount Adams, Mount St. Helens, Mount Rainier, it's why they all exist. Cascade Arc started forming about 40 million years ago and really took on its growth about 20 million years ago. But Mount Hood and even Mount Rainier, even Mount St. Helens, they're not 20 or 40 million years old. The typical lifespan of a Cascade volcano, one of these composite cones or stratovolcanoes, has a lifespan of about 2 million years. I don't know the exact figure, but you can go on Google and look it up through radiometric dating of the andesite. I believe that Mount Hood is about 1.5 million years old. So in the Cascades, a big stratovolcano like Mount Rainier grows, lives for about 2 million years, stops erupting, goes dormant, and then the process of uplift and weathering, that mountain gets weathered and eroded and eventually disappears into what geologists like to call ghost volcanoes. There's several ghost volcanoes that are pretty famous in the Washington Cascades north of here. Goat Rock's Wilderness area used to be a stratovolcano about the size of Mount Rainier. Glacier Peak used to be a stratovolcano, again, probably about the size of Mount Rainier. It's no longer even exists. You can only tell it was there by the geologic formations that are left behind. So Mount Hood is about 1.5 million years old, and it is the result of plate tectonics, the oceanic Juan de Fuca plate, diving under or subducting, as they say in geologic terms, underneath the North American plate.